what I will talk about today is likelihood-free inference, and in particular about approximate Bayesian computation, whose acronym is ABC. So let me start by telling you how statistical inference works. This is an introduction to statistical inference, just to have everybody on the same speed, because maybe not everybody has a background in statistics. So in statistics, we start with some data, which we will label Y, and N is the sample size. And then typically, we come up with a model to describe the data, and the model is indexed by some parameter theta. So theta will be the parameter vector, and we will let D the dimension of the parameters. Y0 or YO will be the observed data. So before the experiment, this is a random variable, and we assume it has this distribution. And then once we have run our experiment or taken our observation, this will be the observed data. It's not random anymore, it's observed. And if we are Bayesian, as I am, we also have some prior probability distribution, which is a distribution over the parameter theta that expresses the information that we might have on the parameter before looking at the data or before running the experiment. This information can come from experts, prior opinion, or previous studies, or knowledge domain expertise that we can incorporate in this distribution. So P of theta is the distribution over the parameters. And with these ingredients, what we would like to get is inference on the parameter theta, because once we have specified the value of the parameter, we will know everything about the model, assuming the model is correct, and therefore we can do prediction or forecasts. We will also talk about model selection, which is a setting where we don't have a single model that we trust, but we might have more than one model that we want to choose between. So the typical probabilistic statement that we want to make about theta are what is the value of theta that has most likely generated the observed data. We might want to build a confidence region for the parameter, or we might want to do hypothesis testing on the parameter. Is the value of the parameter bigger than some threshold or less than some threshold? So let me focus a little bit on the model. The model can be given in the form of a probability distribution function. Okay? If we assume that the data has a Gaussian distribution, the parameters are the mean and the standard deviation, and the distribution of the n observed data, assuming that they are independent and identically distributed as Gaussian, will have this expression. Sometimes, for more complex model, we might not know the normalizing constant of the model that we use, which is the constant that makes the distribution integrate to 1. So the model might be known up to a normalizing constant. So in particular, if the model is Gaussian, the normalizing constant is 1 over square root of 2 pi, which is known for a Gaussian model, but for more complex model, it might not be known. A further level of generality is when the model cannot be written in closed form expression, not even up to a normalizing constant, because it's either too complex or too costly to evaluate the analytic form of the statistical model. But we can generate from the model given a source of random bits. So assuming again that our data is normal, if I give you some value for the mean and the standard deviation, some value of the parameter, and if I give you a source of randomness, so if I can tell you how to generate a normal 0, 1 random bit, then you will be able to generate a pseudo observation. This is not the real data, but it's a data that comes from that hypothesized model, with that given value of mu and standard deviation just by doing this simple transformation of the random bits. So yi will have a distribution from the model that we have assumed. Okay? So models of this form, we call them simulator-based model or generative model. And it's important to stress the fact that we can forward simulate from the model. And there are many models in real science that have this nature. Okay? So sometimes you cannot write down the model in closed form, not even up to a normalizing constant, but you can forward generate if I give you some values of the parameter and a source of randomness. Okay? So today we will focus on this type of models, and I will call them generative model or simulator-based model. Okay? Let me now focus on the probabilistic statement on how we can go ahead and answer this question: do point estimation, confidence interval, or hypothesis testing? Well, we based our inference typically on the likelihood. The likelihood function, which we will indicate with L, is the probability density function of the observed data that we look at as a function of the parameter, theta. And when we do maximum likelihood estimation, we find the value of the parameter that maximizes the likelihood. But we need to have the likelihood available in closed form, and therefore we need to have the model available analytically in order to maximize this likelihood. Similarly, when we do Bayesian inference, we build the posterior distribution, that is the distribution of the parameter once we have looked at the data, which by Bayes' theorem is proportional to the product of the likelihood times the prior. And the Bayesian estimator, if you have a squared error loss function, will be the posterior mean. If you have an absolute value loss function, will be the mode of the posterior distribution. But Bayesians base their inference on the posterior distribution. And since the posterior distribution is the product of the prior times the likelihood, if the likelihood is not available, the posterior distribution is also not available, and we are stuck. So likelihood-based inference, either maximum likelihood or Bayesian inference, as it says, are based on the likelihood. And for simulator-based model, this likelihood is not available. We cannot write it down, we cannot evaluate it at any given point, and therefore we cannot maximize it, or we cannot compute the posterior distribution. So the traditional way of doing statistical inference is not available if the likelihood is not available. So what I will talk about today, and basically throughout the day, we will be working looking at likelihood-free inference. That is, procedure to answer the typical statistical question, point estimation, confidence interval, hypothesis testing, prediction, and model selection, when the likelihood is not available, but in situations where we have a simulator-based model. So we will use this property of the model, that is, the ability to forward simulate pseudo-observation given some value of the parameter, and this property will allow us to perform sound statistical inference. Why do we like this simulator-based model? Well, because they are built using knowledge domain expertise. Because they scale well with data, they allow to use unobservable or latent variables, and they're easier if we want to study the effect of interventions on some of the variables that are involved in the model. There are various ways of making inference when the likelihood is not available. Here are some references. Today, I will focus on likelihood-free inference for simulator-based model, and specifically, I will talk about approximate Bayesian computation as one method to make inference from these generative models when the likelihood is not available. Now, there are very many examples of this type of simulator-based or generative models. For example, in astrophysics, scientists know how to simulate the formation of galaxies, stars, or planets. This is something they know very well how to do. Also, in evolutionary biology, biologists know how to simulate the species evolution. They know the mechanism that govern the species evolution. Similarly, in ecology, ecologists know the mechanism, the microscopic rules that govern the migration or the relationships of different species over time. But those mechanisms interact with themselves in a complex way that knowledge domain experts, biologists, ecologists, astrophysics, or neuroscientists know and understand very well using their knowledge domain expertise. But if we ask them to write down a model explicitly, that's very, very complex. On the other hand, for them, it's very easy to simulate those models if I give them some values of the parameters that index those micromechanisms that they know very well how they work. So as I said, not only astrophysics, biology, ecology, neuroscience, health science, meteorology, but also social sciences. For example, we know how friendships are built, right? We can strengthen a friendship with somebody whom we already know. We can become friend of a friend, or we can become friend of somebody whom we didn't know before. For example, during this workshop, I hope there will be new friendships that will be born between people that didn't know themselves before. So sociologists know very well how friendships form. And those micromechanisms interact and build, for example, a network of friendship that you might then observe through Facebook or through email exchanges. Well, those micromechanisms give rise to a model and give rise to a likelihood, but the likelihood is too complex to write down, but it's very easy to simulate this mechanism of friendship formation. Okay. So the working example that I will use myself and that Rito will also build on this are models that are defined by a system of ordinary differential equation or partially differential equations. But this is just a prototype model of a complex model that can be forward simulated easily, but it's hard to evaluate. Or to write down the likelihood in closed form. In these ODEs or PDEs, we either assume that the model itself is stochastic or that the observations are observed with an error, or when we want to forward simulate, there is a numerical error when we want to solve these PDEs or ODEs. And a typical example of a system governed by differential equation is the brain structure, or the way the brain works. And here you see a simulated neural activity of the cortex of a rat. Okay? And this is a picture that it's obtained by forward simulation. So let's go a little bit more technical into the details. M will be the model, and theta is the parameter that indexes the model. If your model is defined by a system of differential equation, you might have two coordinates, x and y, and you will have two functions that tell you how those two coordinates evolve over time. And each one of those two functions is indexed by a parameter, which can be a vector, and let's call theta 1 and theta 2 the two parameters that govern this system of differential equations. So this is our model, theta is the parameter, and those are differential equations. So you understand that if I give you two values of the parameter, theta 1 and theta 2, you will be able to forward simulate a trajectory for x and y over time. The question is, which values of the parameter give rise to trajectories that are close to the ones that we observed in our data. And this is a challenging problem because the likelihood here is not available in closed form or is too computationally costly to evaluate the likelihood at any given point, because this system is a complex system of differential equation. So in this setting, if we want to make inference on the θ1 and θ2, we will need some algorithm and some statistical tools that is likelihood free. In particular, I will talk about approximate Bayesian computation, and Rito will talk about approximate likelihood, which is another likelihood-free inference methodology. So, well, I told you that I have a Bayesian approach to statistical inference, so let me remind you what the Bayesian paradigm is about. But even if the name is approximate Bayesian computation, there's nothing really inherently Bayesian in the methodology that I will tell you about. But if you're a Bayesian, you have, as I said, a prior opinion on the value of the parameter. If you do not have any information on the possible values of the parameter, you might express a situation of ignorance on the parameter by putting a flat, non-informative prior over all possible values that the parameter can take. So you only need to have a lower and an upper bound for the possible values that the parameter can take, and then your prior can simply be a uniform prior. And throughout the simulation that we will show you today, most of them, we will be using a flat prior, so eliciting a status of ignorance about the parameter. Then you have a likelihood, which might or might not be available in closed form. And Bayesians base their inference on the posterior, which by Bayes' theorem is equal to the product of the prior times the likelihood divided by the evidence, which is the normalizing constant of the posterior. This P of y is the integral of the numerator with respect to theta, so that this posterior distribution integrates to 1. Now, as I was telling you, if the likelihood is not available, the posterior is also not available in closed form. So we can not do likelihood-based nor posterior-based inference. So today we will handle the situation where this is the case. The likelihood is not available, and therefore the posterior is not available. Still, we will base our inference on an approximation of the posterior distribution, and we will build this approximation by using a feature of the model, which is the fact that the model is a generative model. And this is exactly what ABC does. ABC avoids the evaluation of the likelihood because it's too complex or computationally intensive, and uses instead the property of the model, which is the ability to forward simulate from the model given some values of the parameter. And this forward simulation, if the model is complex, we do it on the supercomputer of the CSCS, on the HPCs, and we will show you how we do that. And the basic idea behind ABC is that we want to find values of the parameter theta which generate, by forward simulation from the model, pseudo data. So we will indicate y star with y star the data that is generated from the model by forward simulation given a value of the parameter. So we want to identify the value of theta. We produce simulated data, y star, that is close to the observed data, yo. And to evaluate this notion of closeness, we need a discrepancy measure, a measure that tells you how close y star, the simulated data, is to the observed data. So if y star is close to y0, then we think that the value of theta that gave rise to y star by forward simulation most likely also has given rise to the data that you have observed. This is the key notion behind ABC. So let me repeat this, because this is the crucial step of ABC. So given some value of theta, I forward simulate from the model some pseudo data, some synthetic data. We compare the synthetic data with the observed data. If those two are sufficiently close, we retain the value of theta. So we do this forward simulation very, very many times in parallel on supercomputers, and we filter out the values of theta that gave rise to simulated data that are close to the observed data. And we do that because the intuition is that those values of theta that have generated pseudo data close to the observed data might have also generated the real data. And indeed, they form an approximation to the posterior distribution. So this is a picture that sort of gives me the opportunity to repeat this concept again. So this is nature that gave us some observation. Then we have a model that we believe reproduces what nature does. The model is typically indexed by a parameter or a set of parameters, theta. And the model is a complex model, so complex that we cannot write down the likelihood in closed form. So forget about MLE, forget about the standard posterior or Bayesian analysis. But the model is a simulator model, allows us to forward generate, given some value of theta and given a computer, to forward simulate some pseudo data. So we do this forward simulation very, very many times for different values of theta. How do we choose these different values of theta? Well, if we are Bayesian, we generate them from the prior distribution. If you are not Bayesian, you simply take a flat prior distribution over the set of possible values of the parameter, so you sample from this uniform prior distribution. So you get very many different values of theta, very many different values of y star. Some of those y star will fall inside a ball centered at the observed data of some radius epsilon. Some will fall outside. We retain the values of y star that are within this ball of radius epsilon, that is, whose distance is less than epsilon. And we associate those y star the corresponding values of theta that has generated them. So among all the possible values of theta that are simulated from the prior, we filter out, we retain those values of theta that have generated pseudo data that are within this epsilon ball. Now, we can prove that those values of theta that we have retained form an approximation to the posterior distribution. And therefore, we can use them to do statistical inference, both point estimation, confidence or credible intervals, hypothesis testing, and even model selection, if instead of having a single model, you have more than one possible models for the data. So let's write down this algorithm in pseudocode. So this is the vanilla ABC, also known as rejection ABC. This is the basics form of approximate Bayesian computation. Later today, you will learn more complex ABC and more efficient ABC algorithm. But this is just to give you the intuition and the structure of ABC. So I'm a Bayesian, I have a prior distribution. If you're not a Bayesian, you put a flat prior over the set of possible values that the parameter can take. And typically, knowledge domain experts have a very good idea of a lower and upper bound that the parameters that index their model can have. Given this prior distribution, we sample a value of the parameter. Let's call it theta star. Then we use this property of the model, which is the ability to forward simulate some pseudo data. Let's call this pseudo data y star. Y star is the pseudo data associated to theta star. Then we accept theta star if some distance measure, rho, between the observed data and the simulated data is less than some threshold epsilon. Those values of theta star, the accepted values of theta star, are approximately distributed as the posterior distribution. approximately in epsilon. As epsilon goes to 0, as we shrink this ball centered around the observed data, further and further, the approximation becomes more and more precise. And crucially, this approximation to the posterior distribution is obtained without the need of evaluating the likelihood. We've never used the fact that we need to evaluate the likelihood at any given point. Some of you might be familiar with Markov chain Monte Carlo simulation, like the Metropolis algorithm, the Gibbs sampler, and so on. In all these algorithms, you need to evaluate the likelihood or the posterior at any given point. You propose a value, and then you accept or reject. And in order to accept or reject, you need to compute the acceptance probability, the alpha. And in that acceptance probability, you always need to evaluate the distribution that you are targeting. Okay? If you don't have a closed form expression for the likelihood, those MCMC simulation algorithms that are very, very powerful, because they also work if the likelihood is available up to a normalizing constant, are ruled out, because you cannot compute the acceptance probability. All of them, Gibbs sampler, Metropolis Hastings, and all the variations on them are ruled out. So what I'm giving you is an alternative to those algorithms. Good. Now, if your data is very big, as it happens in many of those applications, astrophysics, social, and biology, and so on, then a direct computation of the distance between the observed data and the simulated data can be unfeasible. Therefore, we might want to introduce a lower dimensional summary statistics, which we call S, which summarizes the data by capturing all the relevant information contained in the data relevant for making inference on the parameter theta. Now, knowledge domain expert might have, and typically do have, opinions on what are the summary statistics that are relevant for making inference in their domain of expertise. So we summarize the data, both the simulated data and the observed data, and the comparison between the distance is done based on this summary statistics S. So instead of using this quantity, we will use this quantity. Now, if the summary statistics is sufficient for theta, that is, it contains all the information relevant in the data for making inference about theta, then we do not introduce a further level of approximation in the ABC procedure. Unfortunately, evaluating whether a statistics is sufficient or not, it's impossible if you don't have a likelihood. If you go back to maybe your statistical course, the definition or proving that a statistics is sufficient requires a likelihood, which we don't have, remember, we don't have a likelihood. So an exact evaluation of whether the summary statistics is sufficient or not is typically very hard. There are some special cases where you can do it, but typically it's impossible. So most of the time we will be inducing a further error of approximation in the ABC procedure. But that's the way it is. We will have to live with that. And the best way to choose the summary statistics is to ask our knowledge domain expert that have given you the model to also tell us about the features of the data that they observe, which they think are relevant for making inference on the model and on the parameter. So ABC, well, the vanilla ABC, the rejection ABC that I told you about, and the more refined approximate Bayesian computation algorithm that you will learn today, paired with models that have this feature of being generative, therefore simulator-based models, give rise to a generic and sound likelihood-free inferential framework that allows you not only to make parameter estimation, but also to assess the uncertainty in the estimates that you get. And you also can do model selection and quantify the uncertainty that you have when you select one of the models that are available to you. So let me put this ABC rejection sampler in the framework of a complex system, which is a system of differential equations. This, as I said, will be my running example. So suppose you have some observed data, which in this case comes in the form of a spatial temporal data set. Then our knowledge domain expert give us a system of differential equations that describe the model that they want to use to describe this data. This model is indexed by some parameter, theta, and we also ask our knowledge domain expert to elicit a prior distribution on the model parameter, which, if they don't have any strong prior opinion on what are the most likely values of the parameter before looking at the data, can always be picked to be uniform over the set of possible values. Then, using the feature of the model, which is a generative model, and given some value of the parameters simulated from the prior, we generate some pseudo-data, which is also comes in the form of a spatial temporal data. The observed data has a spatial temporal structure. The simulated data has the same nature of the observed data, because we then want to compare those two after having summarized them through some summary statistics S, and then we accept the value of theta star if the distance between the summary statistics computed on the observed data and the summary statistics computed on the simulated data is sufficiently small. What are the typical summary statistics that we can use when we have a time series? Well, we can use the mean, autocovariance, cross-covariance, or at different legs. And we'll get more into the details of the possible summary statistics that we will be using. And in particular, the application that I want to tell you about is a real application. The model is a model for weather prediction. It's called the Lorentz 95 model, which is a variation of a model that was introduced in 1995. So we will use rejection ABC, but actually what I will show you are results are obtained with a more refined version of ABC, which is population Monte Carlo ABC. And those alternatives to the vanilla ABC will be introduced later today. So what we need now is, what I need to give you now to do ABC is to specify the model, to specify the summary statistics, and to specify the discrepancy measure. Those are the three ingredients that you need to run ABC. And that's it. This is everything you need. A model, a summary statistics if your data is large, and a measure of distance between the summary statistics computed on the observed and the simulated data. That's it. This is everything you need. And typically, the model and the summary statistics will be given to you by the knowledge domain experts. So the model we will use is a model that was introduced in 1995 and later refined in a paper in 2005. So some of the weather variables are called slow, some of them are called fast. The slow weather variable are observed over time, so you can actually measure them. And in the specific example that I will tell you about, we have 40 slow weather variables that are observed. This will form our Y0, the observed data. And we will have 120 fast weather variables which are not observable and will be imputed. We'll start with some initial values of the observed weather variable. And then we will try to find the parameters of the model that will allow us to do weather forecast for 20 days ahead. So the prediction which correspond to a value of t that ranges between 0 and 4. Now, I don't want you to get lost in these slides, because I get lost myself, but this slide will be replaced by the model that you and your knowledge domain expert know. Okay, so I don't want to go too much into the details because this is a model I've been working on with some knowledge domain expert. Here you will have the specification of the model that describes the problem that you will be working on. But in this case, so this is a system of SDEs. that describe the evolution of the weather variable x over time. And this evolution is a function of other weather variables at the same time point. So we are describing how xt evolves, or xk evolves over time, and this is influenced by the value of x itself and the previous the values of other weather variables. And then there is a deterministic part to the model and a stochastic part to the model. The deterministic part is called G, and this deterministic part has a parameter theta, which in this case, in this model, is a two-dimensional parameter. So it seems a very complex model, but it's really, the parameter space is two-dimensional. And those are the parameters where we want to make inference. And then there is a stochastic forcing term that represents the uncertainty in the model that is determined by us forcing the fast weather variable, those variables that are not observable, which we force into the model. Then what we do, well, this is a system of SDEs. We have to, in order to forward simulate this system, we use a fourth order solver by discretizing the time interval where we are working with. So if I, for example, set the values of the parameter θ1 and θ2 to 2.1 and 0.1, these are the pseudo data that I obtain by forward simulating from this complex model. So it doesn't matter how complex the model is. The important thing is that if I give you values of the parameter, you can forward simulate and obtain some pseudo data. Those are the trace plots over time of this 40 observed weather variable. Then we take this pseudo data. This plays the role of the y star. This is the theta star. And we compare it with the observed data after having summarized this data. So I need to tell you what are the summary statistics. This is the second ingredient. So first ingredient, the ability to forward simulate it, and we have it using an SDE solver. Second, the ability to summarize the data. And in particular, here we use some summary statistics, which is, this is a time series, so which is the mean, the variance, the autocorrelation with leg 1, the covariance of xt with its neighbors, and the cross covariance of xt with its two neighbors for leg 1. Everything averaged over k. But again, I don't want to go too much into what summary statistics we are using for this specific problem. It's important to understand that this is the second ingredient that we need. And then we need, as a third ingredient, the distance between the summary statistics computed on the simulated data and the summary statistics computed on the observed data. And here we simply take a Euclidean distance. So the summary statistics is a 6-dimensional vector. We compute this summary statistic on the simulated data, on the observed data, and if the distance is sufficiently small, less than some threshold epsilon, we retain the value of theta that has generated this simulated data that is sufficiently close in this space of summary statistics to the observed data, the summary statistics computed on the observed data. We do this over and over for many different values of theta simulated from the prior. We get many different pseudo data, we compare them, and some of them we retain, some of them we throw away. The parameter thetas that are retained, that are filtered out from this ABC procedure, gives rise to an approximation of the posterior distribution. As if you are doing MCMC simulation, all the accepted thetas, you retain them, and that gives rise to an approximation to the target distribution. Well, same here. You retain those values of theta. These are the smoothed through kernel density estimator of the values of theta that have been retained from this ABC procedure. This is the true value of the parameter that has actually generated the observed data. This is a simulated setting. So the observed data was really simulated from some true value of the parameter, which we then pretend we don't know. Okay? And we can see how well we are doing. So those are the control plot of the approximated posterior distribution approximated through ABC. And you see that we are doing fairly well, and without the need of evaluating the likelihood in any way. In particular, those are 10,000 samples. So we repeat the ABC procedure until we retain 10,000 values of theta. Okay, we keep doing this until that. These are the two marginal posterior distribution for θ1 and θ2, okay, which we obtained from the accepted theta by marginalizing, looking at the first and the second coordinate of thetas. Those bars are the true values of theta that has generated the data. Well, we are not perfect, but we are consistently estimating the true value of the parameter. I want to conclude, how much time? 4 minutes. Okay, model selection. Okay, so far I've done everything assuming that we have a single model. Suppose you have two competing models, M1 and M2. What do? Well, both models will be indexed by parameters and will have the ability to forward simulate your some pseudo data. Now, we can use ABC to not only estimate the best values of the parameter for a given model, but also to decide which one of the two models best describes the data. And this is very easily done by adding a layer to the ABC procedure that I've told you so far. So this is the ABC procedure I've told you so far. Simulate theta, simulate y star, and retain theta if the distance is sufficiently close. To do on top of this estimation, also model selection, we will add 3 steps in our iterative algorithm, which is the following. So we have 2 models, well actually 3 steps, is actually 1 additional step, which is this red one. Those 2 lines are describing the setting. So we have model 1 and model 2, which describe a system, which are given by a system of differential equations, each one indexed by a parameter and each one having this forward simulation property. And suppose a priori, we have no prior opinion on which one of the 2 models best fit the data. So a priori, we take a prior distribution on the model, which is an unknown. So as a Bayesian, I put a prior on everything I don't know, which is 1/2, 1/2. So if you have maybe a different prior opinion, you might change this prior distribution on the model parameter. Then you simulate a model index. If my prior is 1/2, 1/2, I toss a coin. If it's head, I choose model 1. If it's tail, I choose model 2. Okay? Then suppose I've chosen model 1. Toss a coin, model 1, head, model 1. I simulate a value of the parameter from the prior distribution of model 1 on the parameter space, simulate the data, and do this comparison. Then I start over. I toss another coin. I choose a model, one of the 2 models with equal probability. And then for that model, I simulate the parameter, the pseudo data, and I retain the value of theta if it's sufficiently close, if this distance is less than epsilon. Okay? Now, suppose you do this over and over, and at the end of the day, you realize that all the thetas that you have retained came from model 1. Okay? Then model 1 is the one that is best supported by your data. If, on the other hand, 80% of the theta that you have retained come from model 2, then you would select model 2. Model 2 best describes the data that you are looking at. So this ABC procedure for model comparison, at the end of the day, gives rise to a pairs of parameter value and model index. And these pairs of parameter values and model index that have been accepted by the ABC procedure, filtered out, form an approximation to the joint posterior distribution of the parameter and the model index, given the summary statistics. Then, to do a more refined version of simply counting the number of parameters that have been retained that come from model 1 and from model 2, which is proven to be not very efficient, something more sophisticated is done to approximate the posterior error rate of each one of the model by a random forest classifier. So we train a random forest, and then we classify the observed data, and we see how many times the observed data ends up in model 1 or model 2. And the frequency of correct classification, or better, the 1 minus the frequency of correct classification, is an approximation to the posterior error rate. And then we select the model with the smallest posterior error rate. So this is a more refined and better way of doing model selection with ABC. Okay, so I conclude here. I hope I managed to sort of give you an idea of how powerful this ABC procedure is. Carlo Albert will tell you about adaptive ABC and how to select the summary statistics. And then Rito will continue with advanced topics on ABC by telling you how classification tools can be used to define a discrepancy measure, this row distance, and how you can automatically select summary statistics. And we'll also introduce ABC Pi, which is a Python suite that Rito and Marcel have built, and that runs on the HPCs of the CSCS. Thanks for your attention. Do we have a coffee break, or do we start? Thanks.